Now we'll continue our analysis of the definite integral by looking at one-dimensional motion. We've looked at one-dimensional motion before when we were talking about the derivative. And of course this subject's very useful for those of you studying physics. First thing we'll do is go ahead and examine all the basic properties: position, velocity, distance, and displacement, and how the definite integral can help us here. Let me bring you back to what we discussed before. The three major functions of interest in this sort of physical problem are position, velocity, and acceleration. Now, from what we saw before when we were looking at derivatives, the position function we called s of t, the velocity function, of course, we called v of t, the acceleration a of t, and we learned that you could go from s to v by differentiating. That is to say, the velocity function is the derivative of the position function. And you can do the same thing by going from velocity to acceleration by differentiating. So the acceleration is the derivative of the velocity function. Now, let me also write, since the velocity is the derivative of the position function, write it as s prime of t. The acceleration then is v prime of t, and also can be written as s double prime of t, as the second derivative of the position. Now that's all differentiation, that's all something we've seen before. The question is now, how do you go backwards? Well, we have the tools. We know that to go backwards, we want to anti-differentiate. We want to undo the derivative. So the same thing in this direction, we want to anti-differentiate. Now we have a different word for that now, and we'll use that instead. We'll say that this is indefinite integration. And this is indefinite integration. So there's how we go backwards, and this gives us the whole cycle. So we can go between position, velocity, and acceleration in either order, depending on our needs. Now, what do these actually look like, these indefinite integrals? Well, the first one, to go backwards from velocity to position, is exactly to say that position is the indefinite integral of velocity. We already know this, but it's good to put this all in one place. Then, to go from acceleration back to velocity, it's the same idea. Here, velocity is the indefinite integral of acceleration. So, this pulls together what we've seen now about indefinite integrals. And now, since we want to talk about definite integrals, we'll introduce that idea. But let's do one example on these just to get some practice before we go forward from here. Suppose we have a particle that is moving on a line, and we know that the velocity function for this particle is cosine pi t. Now let's also suppose that we're given the information that the distance s, or position rather, is equal to 4 when the time is 0. So when we start, the position is at position 4. We want to then find the function that defines position. So all we have is a single point for position, and we want to actually get the position function. Well, from what we said on the previous page, the position function is the indefinite integral of the velocity function, because the velocity function is the derivative of the position function, and the indefinite integral undoes that derivative. Well, the velocity function here is the cosine of pi t dt. And then what would have derivative cosine of pi t? Well, sine of pi t would almost be right, but when I take this derivative, I would get a pi out front. There's no pi here, so I would need to have a 1 over pi. And now this will have derivative cosine pi t. And then plus c, of course, because it's an indefinite integral. Now, we can find out what c is because we have some extra information. We are given also the fact that s evaluated at 0, at time t equals 0, the s, the position, is equal to 4. That's given information. On the other hand, here's the position function. So if I put in for t 0, here I get 1 over pi times the sine of 0, which is 0, plus c. So this is 0, so c turns out to be equal to 4. Thus, we have the following. We can write down that s of t is 1 over pi sine of pi t, that comes from here, and then the c we just learned was 4. And there we have recaptured the position function from the velocity function using indefinite integration. Now we want to go ahead and start talking about definite integration, and let's make a little observation to help us there. Suppose now if we look at the integral of v of t, the velocity again, but this time let's put some limits. Let's go from time t0 to t1. So this is now a definite integral, which is a number, instead of an indefinite integral. What would this be? Well, if you're trying to evaluate this using the fundamental theorem of calculus part 1, we want to find something whose derivative is v of t. Well, v of t is s prime of t, the derivative of position. So this will be s of t here, evaluated from t0 to t1. And then by the fundamental theorem, you evaluate it at the upper minus the lower. So that's s of t1 minus s of t0. But wait, I've seen this before. If you take the position at a later time minus the position at an earlier time, you have just discovered displacement of the particle over that time period. Aha! So we've got something now we can write down. This integral now, this definite integral, represents displacement. So let's put it here in the center so we can talk about it. t0 to t1, v of t dt. Now this integral we have just learned, and I'll write it over here, is displacement. And that's a plus or minus number. Remember, displacement can have a negative sign, over the time interval t0 to t1. So this is what this integral is. This integral also, if you just read it as a definite integral, is a definite integral of velocity over that same time period, t0 to t1. So I'll write that on this side. Now I'm setting this up to compare to something on the next page, so keep in mind what we're doing here. Now, if we just look at this as a definite integral, this definite integral for this function v of t represents visually the net area, which can be plus or minus, that is, can have a sign. This is the net area between the function v of t and the x-axis above the interval t0 to t1. And if we draw a little picture to illustrate the idea, let us suppose we have a function v of t that maybe looks something like this. So this would be v of t. It would go from a position here t0 to an ending position here, say t1. And the integral would add together all of these positive and negative areas and get, as a result, a net area. So that's what we get out of this one integral, this definite integral of velocity from one time to another. It is displacement. It's a definite integral of velocity. It represents net area, which would be the sum of these various values, some of which are positive, some of which are negative. Now, there is something other than displacement that we like to discuss in physics. We also like to discuss the total distance traveled, rather than just knowing where I ended up, either positive or negative direction. So, we can extend this idea and also connect it up to what we've done before. If we now look at the integral from t0 to t1 of v of t dt, but instead put absolute value around v of t, look what happens now. First of all, this now represents the distance traveled over that same interval t0 to t1. So this is the distance traveled. This is, of course, a definite integral. But it's not a definite integral of velocity anymore. It's a definite integral of speed. Remember, speed is the absolute value of the velocity over that interval t0 to t1. So this is a definite integral of speed. This integral now, with absolute value around the function, represents the total area as opposed to the net area between this function v of t, and I'm not wrong in not putting absolute value here because this is total area for this function, and between that function, its graph, and the x-axis t0 to t1. So what I mean by that is, if we look in the picture we had before, going from t0 to t1, what happens is there was a part below. That part is now flipped up by the absolute value. Then there was the hump above. Then there was a little piece below, and that's now flipped up. And then the final part that was above. So what has happened by the absolute value, and this is the absolute value of v of t graphed, all of the various areas are flipped up and made positive, and so we are now counting the total distance, which is what this represents here, the total distance traveled by the particle over this time period. So we have the net area and the total area connected to the displacement and the distance traveled. It's a very nice connection. Now let's go ahead and do an example. Suppose we have a car, and this car, say, has initial velocity v of 0 to be 5, and let's say that's in meters per second. Let us also say that this car has acceleration a of t given by the following function, 2.4 times t, just a constant times t. And it keeps that acceleration for 8 seconds. Here are two questions. How fast is the car going at the end of this time, at t equal 8 seconds? And the second question is, how far did the car travel during the 8 seconds? So there are our two questions, and let's go ahead and look at how we might attack these. The first thing is to read the question carefully and interpret the words how fast for part A. How fast means find the velocity. That's how we measure how fast things are. Meters per second gives you the clue. So here's a velocity. So we need to figure out velocity. Velocity is the indefinite integral of the acceleration, because the acceleration is the derivative of the velocity, and the indefinite integral just undoes that. The acceleration is given to us. It's right here. So this is the acceleration, 2.4 t times dt. And then if I do the integration, it's 2.4, the constant stays, t squared over 2 plus constant c. Now we can find out what this constant is because we have some information here. We know that the velocity at 0 is 5 meters per second. So we can write the velocity at 0 on the one hand is 5, that's given. On the other hand, here's a formula for the velocity. I put 0 in for t. That gives me 0 here plus c. So that's going to mean that c is just equal to 5. Thus, I have the velocity. The velocity is now, let's see, 2.4 divided by 2 is 1.2 t squared plus 5, because 5 is the value of c. This is the specific velocity function for this problem. Hence, we can answer our first question is how fast is the car going at 8 seconds? Well, that would be the velocity at 8 seconds, which is 1.2 times 8 squared is 64, plus 5, and that's going to be 81.8 meters per second. So that answers question number, or part A, how fast is a car going at 8 seconds? And to do this, we had to actually discover the velocity by taking the indefinite integral of the acceleration. Now, let's get to a question that involves the definite integral. The question is how far? How far in this context means the total distance traveled by the car. So that involves it going to the right, to the left, to the right, to the left, adding up all those various distances and getting a total distance traveled. No direction is mentioned, otherwise this would be a displacement question. So, total distance, as we learned from the previous page, is equal to the integral from t0 to t1, which is 0 to 8 seconds here, the absolute value of the velocity, which was the speed, dt. Well, we have the velocity from the previous page, so this is the integral from 0 to 8 of the absolute value of 1.2 t squared plus 5 dt. Now, if you notice here, 1.2 t squared plus 5 is going for t equals 0 to t equal 8. Throughout that entire period, this is never negative. So the absolute value is not necessary. Thankfully, we can drop it. So 0 to 8 of 1.2 t squared plus 5 dt. Now we can do the integration. This will be 1.2 times t cubed over 3. We add 1 to the power and divide by that new power, plus 5t, and this will then be evaluated from 0 to 8. So putting the 8 in first and then subtracting away this function here with the 0 in it, we would have, let's see, putting the 8 in here, the 3 goes into the 1.2, gives me 0.4. That's a little bit easier. Then the 8 gives me 8 cubed plus 5 times 8 minus, let's see, put the 0 in, we get 0 plus 0. Well, that's easy. And then this simplifies down to 244.8 meters. So there we've answered the question. The first part, part A, involved the indefinite integral. The second part involves the definite integral. And you can see how they're all working together to help you understand the relationship between position, velocity, and acceleration. Let's continue our discussion of one-dimensional motion and some notions of physics and talk about uniformly accelerated motion. Well, first of all, in the language of physics, uniformly accelerated motion just means for us that we're talking about a situation where we have constant acceleration. So the acceleration function is a simple constant. It's not a function of t in any other way. That's a very simple situation. Well, with that, we can actually go quite far in talking about the velocity and the position function associated with a constant acceleration. For development here, let's suppose that when t equals 0, time equals 0, which is where we like to start problems, let's suppose that the position function at 0 is s sub 0, which is an initial position. And let's also suppose that the velocity at time 0 is v sub 0, which is an initial velocity. Sometimes these are altogether referred to as initial conditions for the motion. And this is the motion of whatever particle or body we're talking about. Now, these initial conditions don't have to be 0. The initial position and the initial velocity need not be 0. They can be positive numbers or even negative numbers. But whatever they are, together with what happens at time t equals 0, this is all called initial conditions. So, if we start out our situation with the acceleration function of t being a, which is a constant, let's see how far we can go with that. If that's constant, then I know that the velocity is the indefinite integral of the acceleration, which is the indefinite integral of this constant a dt, which is just at plus c. Now, I have an initial value for the velocity as 0, which means that v of 0 is, by given information, v naught. On the one hand. On the other hand, it has to fulfill this, so when I put 0 in for t, I get 0 plus c. So c must equal v naught. Therefore, we now have the velocity function as at from here plus c, which is v naught. So under conditions of acceleration being constant, the velocity is that constant acceleration times t plus whatever the initial velocity is. So this is a nice situation. Let's take it one step further and get the position function. Likewise, s of t is the indefinite integral of v of t dt. Now v we had on the previous page. So this is at plus v naught dt. And now we can easily integrate that. Let's see, that's going to be a times t squared over 2 plus v naught t plus c. Now we also know that at 0 the position is s naught, the initial position. That's on the one hand. On the other hand, it has to satisfy this expression. When 0 is put in for t, we get 0 plus c. So c now is equal to s naught. And with that, we can write down that s of t is equal to, let's see, a t squared over 2. I think I'll write that as 1/2 at squared. That's more traditional. V naught plus v naught t plus s naught. And so that is the position function associated with a constant acceleration of a. So let me summarize all of this, because you'll be using this whenever you discuss uniformly accelerated motion in physics. a uniformly accelerated motion, and this is one-dimensional motion, of course, that in this situation, if you are given that the acceleration is a constant, as we've written here, a, if we're given the initial value for the position to be s naught and an initial value for the velocity to be v naught, then the velocity will be, as we discovered it on the previous pages, at plus v naught, and the position function s of t will be 1/2 at squared plus v naught t plus s naught. So all of these, both of these, are derived from this single constant acceleration using the calculus. Now let's look at an example where we put some of this into practice. Suppose we have a situation where there's a bus at a bus stop. So the bus is stopped, and we have a woman running to meet the bus. So the woman runs at a constant value of constant velocity of 5 meters per second. However, when she is 11 meters from the bus, or from the door to the bus, the bus accelerates at a constant acceleration of 1 meter per second squared. The question then is, how long is it for the woman to catch the bus? Now this will turn out to have an interesting answer. So here's the situation. At time t equals 0, when this whole problem starts, which is when the bus starts up to leave, we have this situation. If we have a position graph, say, here's the woman over here to the left, and over here to the right is the bus, just as it's going to start. And at that moment, they are 11 meters apart. Now, we need to determine what the phrase "woman to catch the bus" means. So, woman to catch the bus, how long is it for the woman to catch the bus? What does that mean, to catch the bus? Well, what it means is that at some time in the future, some common time, the position function s sub woman here, the position function for the woman, will have to be 11 meters plus the position function for the bus. See, the position function tells you where you are at a given time t. And then the position function here for the bus tells where the bus is at time t. For them to be at the same time, for this equation to hold, you have to add the 11 meters here because the woman is 11 meters away from the bus. We want to know at what time these will be equal. So we must solve for t. And that will be the time when the woman can catch the bus. Well, let's see. Since we know that the velocity of the woman at time t is 5 for all t, that is to say 5 meters per second, it is constant no matter what time it is. We don't actually have to use calculus at all to find the distance or position function for the woman. Because in the case of constant velocity, position is exactly what you might have learned in algebra. It is equal to velocity, or speed in this case, positive number, times the time. So the distance is equal to this velocity, 5, times the time. Now this only works because it's constant positive velocity. In that case, calculus is not needed. So here we have the distance function, or the position function for the woman. Now we have to get the position function for the bus. We have to work a little harder. The velocity for the bus can be gotten from the acceleration for the bus by finding the indefinite integral as we've done before. Now the acceleration was given to be 1 in meters per second squared. So that means this integral just gives us t plus c. Now we happen to know that the velocity of the bus at time t equals 0 is 0. The bus is not moving at that time. That's given information. On the other hand, when the 0 is put in for t, we have 0 plus c, so that means c is equal to 0. Well, that's easy. Then the velocity of the bus at any time t is just equal to t. Now we're actually looking for the position function for the bus, so we have to do this process one more time. So the position function for the bus is the antiderivative of the velocity for the bus, and that was just t dt, and so that's t squared over 2 plus c. Now we know that the bus at time 0 is at position 0. We've given that information. And if we put 0 in here, we get 0 plus c. So again, c is equal to 0. Oh, and incidentally, I've used c twice here, and that's correct. I used c here, and then I stopped using it. So c at this point becomes free for use again. And I can start and use it again, as I've done here. Some people like to put c1 and c2, but it's really not necessary if you understand that the c has stopped being used here and is being brought or resurrected again for this purpose. So c equals 0. So that means, thus, we have the position function s of t for the bus is equal to 1/2 t squared, because the c is 0. Now we have the velocity and the position for the bus. We're really only interested in the position. With that, we can solve for t to find the common time when the position of the woman is such that she can catch the bus. So that position would have to be 11 meters plus the position of the bus. We have formulas for both of these now. This is 5t equals 11 plus 1/2 t squared. And to solve for t here, this is just a quadratic. Let's just walk through it. This is 1/2 t squared minus 5t plus 11 equals 0. Let's multiply through by 2 to get rid of this 1/2. So 0 is equal to t squared minus 10t plus 22. Then using the quadratic formula, t is minus the b term with the b coefficient of t, which would be 10, plus or minus the b squared, which is 100, minus 4 times a, which is 1 times 22, which is the c. All this is over 2. And if you simplify this, you get either 5 plus the square root of 3, or you get 5 minus the square root of 3. Well, 5 plus the square root of 3 gives you approximately 3.3 seconds. This is a time after all. And 5 minus, let's see, 5 plus the square root of 3, I guess would be the bigger one, so that's going to be 6.7 seconds. And 5 minus the square root of 3 is approximately 3.3 seconds. Now the question you may have is, wait a minute, we got two different times here. What does this mean physically? Well, what this means is that the woman is running, first of all, at 5 meters per second, and she exceeds the speed of the bus at first, and so after 3.3 seconds, she's alongside the door. Now, if the bus is not stopping yet, then she will run past the bus, and then later the bus will catch up with her a second time at 6.7 seconds. So she actually has two chances to catch the bus in case the bus driver missed her at the 3.3 second mark. That's the reason there are two answers here. So there's a nice example of where you can use this to solve a physics problem. Now let's take this uniformly accelerated motion model and modify it just a little bit to give us the free fall motion model. The idea here is that there's really a very small modification. If you are near the Earth, then what we'll do is we'll act vertically here instead of acting horizontally as we did before with the uniformly accelerated motion. We like to draw things horizontally there. Here we'll think of it vertically. And imagine that at time t equals 0, say the position is 0. We're starting at a 0 point. And v0 is some non-zero number. Or I guess I should say possibly non-zero. But if it's not non-zero, you're not going to be moving. And the v0 could be going up or down. Now, in this situation, the acceleration is what's interesting and what puts it into the uniformly accelerated situation we mentioned before. The acceleration is minus g, which is a constant. This is the constant due to the acceleration of gravity of the planet Earth. And the minus is just to indicate that it's downward. That's really a matter of taste. In fact, some people actually make this positive so that the numbers will work out slightly differently. But in our case, we'll take this to be negative. Thus, if we take the uniformly accelerated motion model and put it in this context, all that happens is that the a, the constant that represents acceleration, is now minus g. And we actually have a value for this we'll use later. So in this situation, we have a of t is equal to minus g, which means that v of t becomes minus gt plus v0. So this minus g instead of a here. And s of t is minus 1/2 gt squared plus v naught t plus s naught. This slight modification is what describes free fall motion of objects that are near the Earth. Let us look at an example of this so you can see how this is used in practice. Suppose we have a penny, and this penny is dropped from the top of a 1,250-foot building. Let us assume that the free fall model holds. So we'll assume the free fall model of motion. And this is a reasonable assumption. 1,250 feet is not very far from the surface of the Earth, so this is going to be a reasonable model of that motion. So the first question we can ask, say, is how long until the penny hits the ground? Penny hits the ground. And a second question we could ask is, what is the speed of the penny at impact? So those are two questions that are very interesting. So let's go ahead and look at these. For the part A, what do we want to do? We want to find when the penny hits the ground. Well, that would say the position of the penny would have to be, instead of 1,250, positive 1,250 feet above the ground, we would like that penny to be hitting the ground when the position is 0, because the ground is where we take the position to be 0. So what we want to do here is to find t such that s of t is equal to 0. Well, let's see. In the free fall model, just to remind ourselves here, we're going to use g, and g can be written in meters per second squared or feet per second squared. Since we're talking feet here, we'll talk about 32 feet per second squared. The initial velocity is 0. We're not throwing the penny downward or throwing it up and then letting it drop. We're just letting it go. And the initial position, of course, is 1,250 feet above the ground. The position function under these circumstances is minus 1/2 gt squared plus v naught t plus s naught, which reduces to minus 16, minus 1/2 g is 16, so that's minus 16t squared. V naught 0, so the middle term drops out, plus s naught, which is 1,250. Now we want the position to be 0, so we set this equal to 0, which is what we'll do on this next page. So we set 0 equal to minus 16t squared plus 1,250, and then solve for t. Well, let's see what we have here. 16t squared is 1,250. I bring this over and take the square root, and I'll just write this as a little bit of algebra. And in the square root, be sure and remember that time is always greater than or equal to 0 here, so we only need to take the positive square root, which will then lead you to t equals 25 over the square root of 8, which is approximately 8.8 seconds. So that's how long it takes to reach the ground. Now, we can ask the question, what is the speed at impact? Well, speed is the absolute value of velocity at impact. So that would be the absolute value of the velocity at the time, which is 25 over square root of 8 of impact. So in the free fall model, we know that the velocity function is given by minus gt plus v naught, and we know what g and v naught are here. This is minus 32t, and v naught, remember, is 0. So there's v. We have to evaluate this, so that's all we need to do now. So the velocity at 25 over the square root of 8 in absolute value will be the absolute value of minus 32 times 25 over the square root of 8, and that turns out to be 282.8 feet per second. And if you want to make this interesting for yourself, translate that into miles per hour, and you'll see just how fast that penny is going when it actually hits the ground. Here's an exercise for you. Suppose we have a particle, and this particle has acceleration given by a of t equals sine of t. Let us also suppose that we know that the initial velocity is 1 and the initial position is 0. And don't worry about the units here. Here are the questions. Find the actual velocity function. Secondly, find the displacement over, then I have to give you a time interval. The time interval is from t pi over 4 to t equals pi over 2. And finally, find the distance function, or the position function. And do it in that order. So give that a try. Our first question was to find the velocity. The velocity here, of course, can be gotten by taking the indefinite integral of the acceleration. And the acceleration, you remember, was just sine t dt. And that is what would have derivative sine t, that would be minus cosine t plus c, because the derivative of cosine t, remember, is minus sine t. So I need another minus to make sure I get positive sine t. Now I'm given the information that v naught, the velocity, and this is also written v naught, the velocity at time 0 is given to be 1. On the one hand, on the other hand, it must satisfy this, so this must be minus cosine of 0 plus c. Well, the cosine of 0 is 1, so this piece becomes minus 1. So that means that c is, put the 1 on the other side, so c must equal 2. So I have the velocity function now is minus cosine t plus 2. So that's what you should have gotten for the velocity function. Now the second part was a question about displacement. And we'll use velocity to answer that question. So we want the displacement of this particle over the time period from pi over 4 to pi over 2. Now that is by definition the definite integral from pi over 4 to pi over 2 of the velocity function. Now we know the velocity function, so this is the definite integral from pi over 4 to pi over 2 of minus cosine t plus 2 dt. Well, that's an easy integral. We should be able to do that. Let's see. Minus sine t will have derivative minus cosine t plus 2t. And then this will be evaluated from pi over 4 to pi over 2. And then we put the upper in and then subtract away this expression with the lower. So this would be minus sine of pi over 2 plus 2 times pi over 2 minus sine of pi over 4 plus 2 times pi over 4. And these are both easy signs. The sine of pi over 2, of course, is 1. The sine of pi over 4 is well known. It's 1 over square root of 2. Or you can draw yourself the little triangle to work it out. If you put those together, you end up with pi over 2 plus 1 over the square root of 2 minus 1. That's approximately 1.28. So here's the exact value and an approximation for it. And there's the displacement we were looking for. Finally, we were interested in the position function. Position function can be gotten by taking the indefinite integral of the velocity function. The velocity function, well, we've already done this, haven't we? There's the velocity function. The indefinite integral is right here. And you might say, well, why didn't we just copy it from above and say that this is the position function? Well, the reason is there's a plus c here. And although this part is the same as this part, because in the fundamental theorem of calculus, remember, it doesn't matter which antiderivative you use here. These are indeed the same. But in the case of the actual position function for this problem, the c may not be 0. So we need to find out what the c is. Let's see. In this case, the initial position was actually given to be 0. So if I put t equals 0 in here, I get 0 plus c. So in this case, the c turned out to be 0. But it won't always. And that means that the position function is minus sine t plus 2t. And that's what you were looking for, and I hope that that's what you got also. You remember we had a technique called integration by substitution, and we used it on indefinite integrals. Now we want to extend that notion to definite integrals. So that's exactly what we'll do here. We'll extend the substitution method to definite integrals. And here is the technique. To evaluate the following number, which is the definite integral from a to b of f of some other function g of x times that other function's derivative g prime of x dx. So this is the number we want to evaluate. It's a number because it's a definite integral this time. And just for the record, for this to make sense, we need to have g prime has to be continuous on AB, so it makes part of the integrand continuous, and that f is continuous wherever g exists on AB. That will make this composition also continuous, so the whole integrand will be continuous. But those are technical concerns that don't need to trouble us right now. To evaluate this number, here's what you do. You make a substitution. And again, I'll use a translation box as I've done before. We'll let u be equal to g of x. Then du becomes g prime of x dx. And so far it looks exactly like what we did for the indefinite integral. However, we have limits here, and we need to account for them also. Here is my recommendation to you. Not only do you want to replace u and du like this, you want to go ahead and use the u function. This is a function, remember, u of x equals g of x. U evaluated at b, which is the upper limit here, is going to be g of b, and u at the lower limit here, which is a, will be g of a. This is the total translation box that you need to have. This is the total translation box. And I put it that way because now, unlike the previous case with indefinite integrals, we have these two cases, which gives us a new upper limit and a new lower limit. And so, this substitution, we do this substitution to get, instead of this integral, which is more complicated, this integral, which goes from now g of a to g of b, and is of f of u du. The whole point was to make this an easier integral than it was before. We have now also completely moved from the x universe to the u universe. And unlike the indefinite integral case where when we finish with this we would end up with a function, so the variable x mattered, here the variable does not matter. So by changing everything here to be in terms of u, we can just move forward and not ever have to go back to x. So this is the way I recommend you always do these, and write your translation box. Let's look at several examples to set that up. Here is an integral from 0 to pi over 4 of tangent x times secant squared x dx. Now in this case, it's fairly easy to discover what u ought to be. If u is equal to tangent x, then the du we need is right there. It's secant squared x dx. Now let's take care of the limits also. U at the upper limit, pi over 4, let's see, u is tangent x, so this would be tangent of pi over 4, and that's one of the few tangents you should know. The tangent of pi over 4 is equal to 1. Then u at the lower limit, 0, is the tangent of 0, and the tangent of 0, of course, is 0. This is my total translation box. So now I have an integral that goes from 0 to 1 and consists of u du. Much simpler than the original one. And now we can finish this without ever going back to the letter x. This is a number and we just move forward. This is u squared over 2 from 0 to 1, which means it's 1/2 minus 0, or 0 over 2, which is 1/2. We are now done. There's no fooling around with trying to get back to the original variable because that is irrelevant here. This is the same number that we would have gotten from the original integral, except that this one is a lot easier. So in all of this, remember, always write a translation box. It's a good way to keep track of what you're doing. And always, although you'll see people suggest otherwise, always translate the limits so that your integral becomes totally in terms of u. So you can really forget the past if you've done this correctly at this point and just move forward. Let's look at another example. Here is the integral from 2 to 5 of 2x minus 5 times x minus 3 to the 9th power dx. Again, this is not so hard to find what u is. We want to work on changing the limits, though. If u is equal to x minus 3 here, recognizing that we have some funny term here with x's in it, let me also note that if u is x minus 3, that means that x is u plus 3, just moving the 3 over. That will come in handy in a moment. So if u is x minus 3, then du just becomes dx. That's nice. Then u at the upper limit, 5, becomes, let's see, 5 minus 3 because u is x minus 3, and that's 2. And then u at the lower limit becomes 2 minus 3, which is minus 1. And now one more thing before we leave the box. I have to deal with 2x minus 5 because I haven't replaced it anywhere here. So 2x minus 5 can now be written as 2. X is u plus 3, so that's u plus 3 minus 5. Let's see, that's 2u. I get a 6 minus 5 plus 1. Now I have my total translation box. It's a little bigger this time, but it has everything I need. And now this original integral becomes, let's see, minus 1 to 2. This becomes u to the 9th times du, but the 2x minus 5 becomes, let's see, 2u plus 1. And then the dx and the du are the same. This is easy because I can just multiply it out, and I have 2u to the 10th plus u to the 9th. Those are just powers, so the integral becomes 2 times u to the 11th over 11 plus u to the 10th over 10, evaluated from minus 1 to 2. That can easily be checked. I'll let that be something for you to do, and in the end you should get 474.8. So there's a couple to give you the sense of how you should write your translation box and keep track of little things like this 2x minus 5, which is not immediate. There's a little bit of work to be done here, a little algebra. Let's do one more example of something a little bit different. 0 to log 3, this integral e to the x times 1 plus e to the x to the 1/2 power. In this one again, it's fairly easy to guess that u ought to be 1 plus e to the x. So du then becomes e to the x dx. And I notice I have e to the x dx, so I have perfect du. Let us change the limits. So the u of the upper limit, u of log 3. Now that looks complicated, but watch what happens. U is 1 plus e to the x. So this is 1 plus e to the log 3. Of course, the e and the log undo each other, so this becomes 3. 1 plus 3, which is 4. Then u of 0 is 1 plus e to the 0. E to the 0 is 1. 1 plus 1 then is 2. And so there's my translation box, which leads me to this integral, the integral from 2 to 4 of u to the 1/2 du, because this part is u, and the e to the x dx becomes du. This is now, adding 1 to the power gives me 3/2, so this will be 2/3 u to the 3/2 from 2 to 4. That's 2/3. I like to pull constants out rather than leave them in here as I'm working, so I put this here. Then I just need to put the 4 into the u to the 3/2. So 4 to the 3/2 minus 2 to the 3/2. And you can stop there if you like. You can maybe go a little further and rewrite this as 1/3 times 16 minus 4 square root of 2. But either case will give you a final answer that's correct. And now you've got several examples where you see how we build this translation box and that we always translate the limits to end up with a simpler integral that we don't have to ever look back for. We never went back to the original once we were done the translation. Keep that in mind. Let's look at some exercises. The first one is for you to evaluate the following definite integral. Minus 1 to 4 of x over the square root of 5 plus x dx. It's your turn to try it. Let's see here. I think u should be 5 plus x. That seems like a reasonable choice. 5 plus x down here will give me a simple u, and we'll see where everything else plays. I see that I have an x here, so maybe I'll also write that x is equal to u minus 5, just in case I need it. Now, u is 5 plus x, so du is dx. Well, that's nice. And then u of 4, which is the upper limit, is 5 plus 4, because u is 5 plus x, and that's 9. And then u at the lower limit is 5 minus 1, which is 4. That completes my translation box, which means this becomes the integral from 4 to 9 of u to the minus 1/2, because this is u down here in the square root and it's on the bottom, times x here, which we discovered is u minus 5, and then du and dx are the same. So this becomes the integral from 4 to 9, multiplying this through. We have u to the 1/2 minus 5u to the minus 1/2 du. And we can go ahead and integrate this easily enough. We add 1 to the power. Let's see, that'll be 2/3 u to the 3/2 minus 5. Add 1 to this power, we get 1/2. So that'll be 2 u to the 1/2 from 4 to 9. And if you put those in, and I'll let you do that, you should have done that yourself. You put the 9 in, and then you subtract away this expression with the 4. You should have ended up with 8/3. And I hope that that's what you did get. Here is a second problem for you to try. Evaluate the following indefinite or definite integral. 1 to the square root of 2 of x times e to the minus x squared dx. Let's see how that one turns out. On this one, I think I'm going to let u be equal to minus x squared. See where that leads me. Du then would be minus 2x dx. Now let's pause for a moment and see if I have what I need. X dx is here, so I have that part. I don't have the minus 2, but I'm not worried, because you remember, I could imagine writing a minus 2 in here and compensating by having a minus 1/2 out here, because minus 1/2 times minus 2 is 1. That wouldn't change anything. So there's my translation so far. I need to do the limits now. U of square root of 2, let's see, that would be minus square root of 2 squared, which is 2. So it's minus 2. And then u of 1 for the lower limit would be minus 1. There's my translation box. Nice simple one. This now becomes the integral from minus 1 to minus 2. This becomes e to the u. X dx, and remember, I had to put a minus 2 in here to get du, which means a minus 1/2 out front. Don't want to forget that, minus 1/2, and I have du. So this now becomes minus 1/2 e to the u, from minus 1 to minus 2. The indefinite integral of e to the u is just e to the u. This is the only function for which that's true. And now this becomes minus 1/2 e to the minus 2 minus e to the minus 1. And you could approximate that if you want, but you might as well just stop there. And I hope that this is the form that you got this in, because that is correct.